myself and CPI. NARUC is a nonprofit that represents the state utility commissions in all 50 states and US territories. And if you'll go to the next slide, within NARUC is the Center for Partnerships and Innovation, which is a grant-funded team that provides technical assistance to NARUC state commissions. And one of our goals is to try to get ahead of emerging issues and connect commissions with expertise and strategies to help inform their decision-making. And one of the ways we try to do that is through events just like this innovation webinar series. And so very quickly, before I introduce our moderator, I wanted to go through the format of today's webinar, as it'll be a little bit unique and interactive because we'll be using Zoom's polling feature. So throughout the course of the webinar, we will present everyone with a couple opportunities to vote, and the responses that you put in will impact the results of the tool that our guests are demoing here today. And once those votes are in and the tool's running, we anticipate it may take a couple of minutes. So while the tool's running, we're gonna try and take some questions. And so feel free to leave some questions in the Q&A box and we'll answer those at that time. So now, if you'll go to the next slide, I'll introduce our moderator for today's innovation webinar, Commissioner Katherine Peretick of the Michigan Public Service Commission. Commissioner Peretick has been serving on the commission since January 2021, and prior to her appointment, she worked in energy storage and technology development at organizations such as NRStor, General Compression, Vestas, the Pacific Northwest National Laboratory, and NASA's Jet Propulsion Laboratory. Thank you again for moderating today's panel, Commissioner Peretick, and I will pass it on to you.
Thanks so much, Sarah. And thank you to everybody for joining as well. As Sarah mentioned, I'm Katherine Peretick, and I'm a commissioner for the state of Michigan. As she also mentioned, I have a background in energy storage. I spent almost 10 years in energy storage prior to joining the commission last year. I can tell you that 10 years ago was way before energy storage was cool. I worked both as an energy storage project developer as well as an engineer inventing new compressed air energy storage technologies. And that's actually what is on the wall behind me, the artsy pictures of a pressure vessel, an electrical panel, and a high pressure valve from a compressed air energy storage demonstration project that I helped to build in West Texas. I've seen the energy storage industry really transform over the last 10 years, from starting off with confusion to curiosity to excitement to now, when it seems like almost all the players in the energy world understand the value of energy storage and that what it can provide to the grid, and that everyone wants to try to find the right opportunities to deploy storage strategically. And that's really where I'm hoping that this webinar today will be able to help out. I've been working in Michigan to ensure that our utilities and our commission staff are thinking about how to best incorporate energy storage into system modeling, particularly for long-term integrated resource planning. We've received some technical assistance from the DOE for help from experts from Argonne National Lab and from NREL to help our commission with this, and have found that engagement incredibly helpful, and which is how I was really introduced to the EPRI DERVET tool that you all are signed up to see demonstrated today for energy storage planning and modeling. This is the most registrants that we've ever had for an innovation webinar. So thank you all for your excitement and for voting prior to the webinar on which cases that you are interested in seeing demonstrated. I wanted to make sure that we're providing information that's useful to you and that you will actually find interesting over the course of the next hour. So long duration energy storage and managed electric vehicle charging were the two options that were voted prior to the webinar with the most votes. So that's what our EPRI team is going to demonstrate with the tool today. And as Sarah mentioned, you'll have the opportunity to continue to shape the direction of the demonstration in a way that is most useful to you and to your state's interests throughout the webinar. There will be periodic polls that will pop up over Zoom that will allow you to choose the model inputs in real time and affect the outcome of the model runs. So as those models are running, we'll use that downtime for Q&A. So feel free to type any questions into the Q&A feature at any time prior, and I'll jump in and ask them of the panelists when we get to that time for questions. So I'm excited to see the cases that you all chose to run in real time and understand how we should be thinking about energy storage planning into the future. So with that, I'll turn it over to the EPRI team to explain more about energy storage modeling and start walking us through the real-time simulation.
Thank you, Katherine. As you mentioned, we're going to focus on some live and interactive demonstrations of the DERVET tool that we've been developing over the past several years. But before we do that, I don't think all of you are familiar with it, so I'm going to give a really brief background, lay of the land of what the tool is all about. And then I'm going to have my colleagues, and especially Miles Evans, walk through the demonstration with you live, and also work with you on doing kind of the choose your own adventure type of demonstration, where you'll get to give some input into what selections we put into the demonstration. So if we go to the next slide, what we can show here is where I like to start out of why we started developing this tool. So we have a lot of different state agencies on the call, but this particular model and tool was funded by the California Energy Commission to be open source. So we're excited to bring this to you today, and for you to have access to it, and for everyone in the public too as well. There were some things that we thought of when we were proposing how to build out this tool in terms of challenges and gaps while we were in specifying the tool. And the main things are, and more than ever today, is that storage, DER, and microgrid deployments really demand robust planning and doing it in a strategic way so that we can make informed decisions, because they are challenging and complicated and complex types of projects. And because of that, some of the things that you might be aware of is that, especially with storage and some of the other DER and microgrids, it requires a project level application and location analysis. And DERVET is really that. So it's a project level technical and economic analysis tool. It can be paired with other types of tools to be kind of just one tool in the toolkit to do more system-wide analysis, like with power flow and production cost modeling, depending on what types of grid issues you're trying to address. But at its core, DERVET alone and running by itself is a project level analysis tool. And another challenge is that, when we put all these things together in terms of the types of applications that storage with other DERs or storage enabled microgrids have to offer, it creates a complex co-optimization problem in terms of technology constraints and benefits, as well as what types of customer and grid or grid services you're trying to provide with these technologies. And then, of course, there's multiple perspectives. So the technology, especially storage, could be integrated at the customer site, either in front of or behind the meter at the customer site, distribution connected, transmission connected, or generation co-located or hybrid type systems. And DERVET addresses all those types of grid domains all the way across the spectrum, as well as looks at the different perspectives that might be available at those different domains. So it could be customer perspective, could be the utilities perspective, or the ratepayers perspective, or some combination, depending on if you're sharing the benefits of the project. So if we go to the next slide, I give a little bit deeper dive into, what are some of the benefits that we think that DERVET provides to stakeholders. So, one of them is addressing those gaps that we identified on the first slide in terms of what tools were available when we started developing DERVET, and we think that we've really addressed a lot of those in terms of giving very detailed and robust project level analysis of storage and TERs and microgrids, but also with the tool being open source and freely available to the public, it really creates a common communication tool among all the stakeholders, so that from addressing issues either in a public forum or at a regulatory proceeding or at a utility level, trying to either create a fair process for an RFP or responding to RFPs, and also communicating between developers and customers, what the value is, and doing it in a way that both sides or both stakeholders can use. And then I mentioned this before, that it's a multi-perspective tool. So of course, across all the different grid domains, from customer to transmission and generation and everything in between, but also looking at it either from the customer perspective, the utility and ratepayer perspective, or a combination of both at the same time. So if we go to the next slide, you'll see just a little bit more background. So, we launched this tool in 2021. So we've had it out for a little over almost a year and a half now. We got over 1,000 users. And before that, we had a beta version where we got a lot of feedback from different stakeholders. And even going further back than that, the California Energy Commission back in 2014 to 2016 funded the predecessor tool, which just focused on storage, which is StorageVet. And even further back than that, EPRI over a decade ago was working on tools that weren't open source, but we were using with our utility members and with regulators. And one example was the predecessor to StorageVet, which was ESVT, which we used with the California Public Utility Commission to do some stakeholder workshops and help to inform the proceeding that eventually led to the procurement targets back in 2013 in California for energy storage. So if we go to the next slide, I'm going to briefly go over a few things just to kind of get you ready for what Miles is going to show you in the live demo. But at the highest level, you can download the tool today at www.der-vet.com, and I think we'll put that into the chat to make it a little easier for you. But the key thing is that you can download the tool and almost get it up and running immediately on your own machine. There's a nice graphical user interface to walk through setting up a project. And then getting the results and also being able to download those. And then we go to the next slide. There's a lot of different technologies that we can apply to a case in DERVET. But today, since we're trying to keep this to an hour, we've kind of narrowed it down based on the voting to looking at a long duration storage system. And we picked so the batteries, flow batteries, and a couple others, and then also the EV case. And with the EV case, there's also the interconnection constraint that we're going to be kind of zeroing in on as well. So we go to the next slide. In addition to the technologies, we also have the services. So I won't go through this full list, but there is the customer, the transmission and distribution grid services, and also the bulk market services. And today for our cases, we're going to keep things pretty straightforward, and so we can fill in the hour and not go over, is just look at a couple services, and pretty straightforward ones that are energy time shift and resource adequacy capacity as well on these cases. So if we go to the next slide, I think what the next thing we'll be doing is, you know, in a minute is going to Miles to give us the actual live demo. But as I mentioned, you can go to our website today, download the tool for free and install it. There's lots of resources on the website too, even if you don't download the tool. So we have reference case examples, help forums, places to provide feedback and questions directly to us, videos, and of course a user guide. And then we also have regular meetings that you can find out more information on the website too, where we leverage EPRI's Energy Storage Integration Council, which is also open to the public and free. And we have monthly task force meetings about DERVET, where we help users use the tool and present new features as we continuously improve the tool, and also get feedback from them in real time about how we can prioritize and you know, address some of the features that they'd like to see in the future. So I think with that and the next slide, I will hand it over to my colleague Miles to start demonstrating the tool. And please do continue to send in your questions as we're going through the demonstration.
Thanks, Giovanni. So to start us off here, before I share my screen with the tool on it, we need to collect some polling info. I was thinking that given our two topic areas today, long duration energy storage and electric vehicles, we should start with the long duration storage case and then can add electric vehicles in a moment. So the poll question that we'll ask right now is about what kind of energy storage technology should we model in this first case. And as Commissioner Peretick said, as we receive responses to this poll, that will influence, you know, how we do the modeling coming up in a moment here. So our options here are an iron air battery, a flow battery, or a thermal energy storage system. So these, you know, for the flow battery and the thermal energy storage system, we've selected an 8-hour duration. And the iron air battery, we've selected a longer duration, and just put in very generic non-vendor specific inputs for these technologies. And as soon as we've collected a good set of responses, you can let me know which technology option was most favored here, and we'll get going.
It looks like flow wins, Miles.
Very good. Let's do flow. So I'm going to share my screen now with the DERVET tools graphic user interface. And as Giovanni said, this is the exact same thing that you'd get if you went to the website right now and downloaded this tool. The difference today is that I've set up an existing analysis here already beforehand that I will load into the tool right now. For the flow battery. Because I saved this case in the past, all the inputs are already populated, but we can go ahead and take a look at our case in a little bit more detail here. So this first page here has some things that are pretty relevant to the general case that we're modeling here. Since this is a project-focused modeling tool, we have to do things like set an analysis horizon for ourselves, that after which we don't consider any costs and benefits. And then as we work through the tool, we will tell DERVET what our DER are going to do, what the DER are, give all the data and specifications that we need to run a case, and then interact with the results at the end. So in our case, I've set an analysis horizon of 20 years for our flow battery here, assuming that's roughly the lifespan of our generic flow battery. And when we add electric vehicles in, we'll probably just consider the same analysis horizon with that as well. Yeah, I'll, for the sake of time, skip over most of these, project setup type inputs and just get into what we're doing with our DER. And in our case right now, we're going to start by just looking at the flow battery. And as Giovanni said, we're going to be mostly participating in the energy market, and we'll see where we get data for that in a moment. And we're also going to be providing resource adequacy capacity in a capacity market area as our sort of simple base case here. One of the options that DERVET offers users is to optimally size equipment in our DER mix. And this just explicitly includes the size variables for these technologies in the optimization problem that the tool solves normally to generate results. We're not doing that right here, so we'll fix the size of all of our equipment known beforehand. And then we can, the next input there, the optimization horizon, tell it that we'll just break up our data into month-sized chunks to speed up our solve time on the optimization. We have a lot of other options for services here that we could be doing in other cases. Up here at the top, the main other way that we could get an energy price into the tool is through a retail tariff, power purchase agreement, et cetera. And DERVET is connected to the OpenEI United States Utility Rate Database, which has pretty good coverage of United States-based utilities and retail tariffs that they offer, and can populate DERVET directly with that database. You don't have to enter anything manually. There is a manual entry option as well. We could also be doing microgrid services, reliability in this case. We could do bill reduction through demand charge management as well, participation in a demand response type aggregation program, or other wholesale market services, ancillary services, et cetera. The other options here are grid support, which we've identified as the deferral service for deferring upgrades to transmission or distribution equipment under a growing load scenario or a growing need scenario. Or we also can construct a service ourselves in the graphic user interface here in case none of those fit what we need to do. But for us, energy market, wholesale participation, and resource adequacy capacity. The next step is to tell DERVET what DER we're going to consider here. We have a big set of options here that can be sort of flexibly combined into a suite of DER that are all part of the same project. These include traditional generation of a couple different types, solar photovoltaic or wind for intermittent generation, energy storage systems, a couple of different kinds of electric vehicles that we'll get into in a moment, and demand response or controllable load. For our first case here, I loaded this case in with a fleet electric vehicle technology option here as well, but for now, let's deactivate that and we'll get some polling going around that in a moment. I'm sure everyone here is aware of the recent developments with the Inflation Reduction Act and other things like that, which can provide extra benefit for storage systems or extra incentive for storage systems that might be located in an area that could benefit disadvantaged communities or that kind of thing. And while that's all still evolving as we speak, what DERVET has built in there right now currently for that sort of thing is the CalEnviro screen results, which express as a function of the census tract in California, California only, a score representing various features of the local community and establishing eligibility for certain programs. So this kind of feature as we go forward could be useful nationwide, perhaps, if that becomes an important part of this. So this doesn't play a role in our case right now, which we're about to see is located in New York, but this is an option here. So now that we've told Dervet basically some high-level project information about where our system's located, how many years we're looking out into the future, that kind of thing, what technologies we're going to consider in our case, which for us is just a flow battery right now, and what that flow battery is going to be doing, we now get to specify all of the technical specifications and data and everything else that the case needs to run. I'm going to not focus on some of these areas and focus more on others. In particular, let's take a look at the energy storage system specifications that we have for our flow battery. So as we mentioned before, for this demo, we're just doing a fixed size analysis here. So we already know the power and energy capacity of our flow battery here, and that's not going to be provided by Dervet. But what we have is a 400 megawatt hour, 50 megawatt system here, so 8-hour duration. Dervet offers the ability to model systems with different charge and discharge power capacities, as you know, especially for some long duration technologies is relevant. But in our case, we just have the same charge and discharge power capacity. We also, for our flow battery here, are assuming a fixed constant round trip efficiency of 63%. Another feature that we might see in some other storage systems or flow batteries potentially are limits on the state of charge, but these are particularly relevant for lithium-ion battery systems, for example. But we've set an upper limit of 100% state of charge and a lower limit of 0%, just meaning that all 400 megawatt hours that we're modeling are usable. So we're not considering any kind of derating there. We also have a target state of charge of 0%, which for us just means that we'll start the year at 0% state of charge and start charging from there. And also, since we selected monthly optimization windows, every month at midnight, we'll also return to 0% state of charge. Our flow battery is going to have a 0% per hour self-discharge rate. And for our case, we'll see a fair amount of cycling, and this won't play a huge role even if we did include it, I think. But for some technologies that have a higher self-discharge rate, this can make a big difference, or that only cycle a little bit in their use case. It can make a bigger difference. But for us, 0% is our assumption for now. We're also not going to constrain how many cycles per day we can do. For a technology that degrades significantly with cycling, like lithium-ion batteries, for example, we might see a limit on daily cycling as a component of a capacity guarantee contract or another stipulation that limits how much we can use the battery. And this is the way that we can pass that constraint into Dervet, or if we want to just modify how much it degrades, we can do that with this as well. But for our flow battery, we're just going to let it go wild. No constraints there. We're also not going to use the degradation model built into Dervet because that is based on lithium-ion degradation mechanisms and outcomes. So this degradation model will, only change the usable energy capacity of our storage system, and it won't degrade the power capacity, for example. So it's a little bit, doesn't fit very well with a flow battery here. We're also going to ignore lots of things, but in particular here, the housekeeping power or other AC electric load that is consumed by the system. And we know that for flow batteries, this can be lots of things, including pumps and whatever else to keep fluid circulating that change as a function of state of charge and that kind of thing. So this modeling, again, isn't internal to Dervet. So we'll just consider, our housekeeping power to be negligible in our case. We put in a capital cost here that is a very generic flow battery number for our size. We'll see how that plays out in the results, but that's certainly something that can be changed. We also put in a fixed O&M cost based on our best approximation of what that is. But again, this is pretty variable for less implemented technologies like flow batteries and uncertain. The variable O&M cost we have is 0. And this one is actually quite relevant for how storage systems operate in Dervet because it is part of the optimization. So if we see a high variable O&M cost, that will suppress the amount of cycling that our battery does because it's trying to minimize the variable O&M cost as well as everything else. So that's a great way, if you have the degradation model turned on in the tool, to manage degradation. If you just increase that cost, you can suppress cycling a little bit and find an optimum value in the middle there. We have a bunch of other inputs down here that we have for every technology in Dervet that are used to help marry cases where there's a different technologies being installed in different years with different lifetimes. And maybe some of those technologies we will replace when they reach their end of life, and maybe some of them we won't. And all of these very complex, project-specific information. But for our case, we just have one technology, so these aren't as relevant. We're constructing our flow battery in the year before it starts operating, and it runs for 20 years, same as our analysis horizon, and everything's good. Okay, so that specifies our flow battery pretty much. Our key specifications we went over, 63% round trip efficiency, no self-discharge. Right now, the model will consider our flow battery to be able to charge or discharge flexibly from its maximum charging power all the way through its maximum discharging power with no minimum power or anything in between that would cause, a step in that. So we're considering this to be very flexible right now, though some other technologies, especially for some long duration storage systems, might not have that feature. They might have a minimum charging power and a minimum discharging power. And those kinds of things can be handled with Dervet. But for our case, we're considering this to be flexible. The other two areas I want to focus on with the inputs here are the resource adequacy inputs and the locational marginal pricing for energy at our node here. So let's go into that first. As I mentioned before, we are modeling a case here in New York State on Long Island. So what we did was pull locational marginal prices from Long Island for the year of 2021. And then our project starts in 2022. So those prices were just escalated a little bit from last year to this year so that we had a full year of data. And as we can see in the plot here, this data or this energy price signal varies from about 0.05 cents per kilowatt hour up to 5 cents per kilowatt hour up to 30 cents per kilowatt hour, a little bit more. So nothing too crazy here. We see some variability, some spikes in the energy price in August especially. So we'll highlight this as a place to look at in the results. But yeah, nothing too crazy here. We get this data into Dervet just by uploading a CSV. You can download a sample right from the tool here. It's pretty straightforward. The other set of inputs here are for the resource adequacy capacity service. And how we handle resource adequacy in Dervet depends on the location. In a state like California, where meeting a resource adequacy need is usually done through a must-offer obligation into the energy market, meaning that participation in the energy time shifting service in DERVET would be pretty much all we need for meeting our resource adequacy obligation. There could be places where there are more stringent requirements. So what I've done here is to tell DERVET that regardless of what the energy price is, I would like our flow battery here to discharge during the 21 peaks in the year, the system load peaks in the year for New York, or for Long Island even rather. So this will just make sure our storage system is providing energy during those system stress times, and is just a way of modeling that. We also give it a capacity price just as an input here. And the capacity price that I selected was the maximum for 2021. So we're getting sort of the most resource adequacy value or payments that we could expect from the system in 2021. The other inputs here are less important. We did give it a system load information for Long Island, which will help that resource adequacy service identify the peaks in the year and make sure the storage system is providing power during that time. And then the other thing here is an interconnection constraint that we're not considering for now. When we're done defining all these components, we can run the case. And this one should be just a few seconds here, but maybe a good time to stop and answer any questions that have shown up.
Yeah, Miles, maybe I can take one about different technologies. So one thing that we didn't mention is that we're working with the California Energy Commission to do a follow-on project that will increase the number of technologies, and to specifically look at long duration storage and really get into the nuances of many different technology types on the long duration front. So it will include non-battery, very non-commercial lithium type technologies that a lot of times are analyzed today. Everything from concrete thermal storage to liquid compressed air and everything in between on that, and also looking at the services side of long duration as well. And Miles kind of mentioned this, that you can put in price streams, but we used historical for this case because we want to keep it real simple to do. But we can also include, inputs, or I should say outputs from other tools as inputs to DERVET, such as production cost modeling or capacity expansion modeling, where we look at macroeconomic scenarios, 20 years down the road that include deep decarbonization, electrification, and things like that. And then we can use those in the analysis as well.
Sounds good. We can move on here then, and to the anonymous attendee who asked about emissions benefit. That's also an ongoing area of development here. Right now, you could do that by just changing the energy price signal if you'd like to consider the value of emission savings. But we're working on other ways of incorporating that more seamlessly. So we ran our results here, and the first thing we're presented with is the very high level summary. We can see from our financial summary here that for our case, the costs exceeded the benefits to our project here. We didn't talk much about the perspective we were adopting, but you could consider this to be the perspective of a merchant third-party type organization who's paying for all the costs and receiving all of the benefits here. Very simple. We'll dig down a moment into where these cost and benefit categories break down to. But the other high-level summary we have here is a heat map of how we're operating our flow battery. Here, the day of the year goes along the x-axis and the hour of the day on the y-axis, where morning's at the top and evening's at the bottom. And the color yellow means discharging, the color purple or blue means charging. So we can see a fairly predictable pattern here where we're charging in the early hours of the morning, discharging in the afternoons with a little bit of variation throughout the year in timing. And if we zoom into the August timeframe here, where the energy prices were the highest, we can see that there's sort of a weekly pattern too, where the weekdays on peak were really discharging the most. But quickly drilling down here to take a closer look, let's go into some time series plots here. Where we can see what's going on. And let me actually just zoom straight to August. It's July, August, there we go. So here we're presented with a lot of data. All this data is now saved to my computer because I ran the case as CSVs. So I can interact with this however I'd like, but we do offer this little visualization here. We're looking at the whole month of August. We can see in the orange here the energy prices and when they spike during the week. We can also see how our storage system responds to that in the purple here, right above it. If I zoom in on maybe the peak couple of days here, we can see that our storage system is discharging fully during the duration of that peak. It even stops a little bit and then starts again with the little extra peak in energy prices there, and then goes to zero and starts charging during the trough in the energy prices, pretty much as we'd expect. Our state of charge during this time of year is doing almost a full depth of discharge cycle during all the weekdays. But as we saw in the heat map, it's not doing it on the weekends because there's not enough price variability or system need for the resource adequacy service to warrant that. We can also see the energy price heat map down here and just how it aligns with the charge discharge heat map that we saw before. And it pretty much aligns with the energy prices as we'd expect. We can also look at the financial results here in more detail. We have now the costs and benefits broken out over the 20-year life of the system by category. So our costs here are the capital costs and then some fixed operation and maintenance costs as well. And our benefits will be that resource adequacy value, which was the maximum that we could expect in 2021 over all years of all 20 years, just sort of escalated slowly and then discounted back to present. In one of the inputs that I mostly skipped over there, I put in a discount rate of 7% if you're interested. And then the other benefit is the energy time shifting benefit, the charging low, discharging high price times. So we are short by some margin, but we could potentially look at other services to fill that gap, ancillary services, distribution or transmission upgrade deferral, anything else that you might do with storage system. And the nice thing about a tool like Dervet is that it will stack in all those services properly, capture the trade-offs. Adding in another service might decrease the value of our existing services, but increase the overall value, that kind of thing. And we also get a tabular view of the annual cash flows in nominal dollars that we use to create that plot up there. So why don't we extend this case with some electric vehicles for another moment here. So this is where our next poll question can come into play. And we can choose between a couple of different types of electric vehicles that we want to add here. One of them would be a single DC fast charger, and actually given the scale of our battery, I think this will be a set of DC fast chargers operating on a predictable schedule, as you might expect in an off-road electric vehicle charging application, or maybe buses or things like that, just so we can get the scale up to our same 50 megawatts here. Or a workplace charging plaza that has a much more smooth electric vehicle charging profile. We can add either of these to pair with our flow battery and see how they interact. So when we have enough responses here, we'll add that in and keep going.
I also think, Katherine, if there are some questions that you've seen that you'd like us to answer during this case, if you want to point those out. I know a couple have come in. We jumped in before to get a few, but feel free to let us know where to zoom in a little bit more as we go through this case.
Okay, yeah, absolutely. I think you've been keeping up with the questions pretty well.
All right, what are we looking like? Are we a single EV or a fleet?
It has been going neck and neck miles, like we're at about 50-50, but in this moment, Super DC Fast Charger wins by 1%, 51 to 49.
Okay, let's do that then. So to add in our one Super DC Fast Charger, let's go into our technology options here. I had already loaded up our fleet EVs, but let's ignore that and add a single electric vehicle here. So now if I go up here, we have our flow battery and a single EV. And now we get to together live here specify this. So this will be our DC fast chargers here. And I'm just going to put in some numbers here that will work well with our case. They might not be exactly right, but let's say we're going to charge 100 megawatt hours per day at a maximum of 50 megawatts. Let's say we can go all the way down to 0. And I don't know, let's plug in at 5 p.m. and be done charging at the end of the day. I'm just going to fill these in really quickly. Not going to model the costs for this, just the operation. I'll have it be the same construction time and lifetime as our battery. And then we're just going to ignore all of these other inputs for the moment here. I'm not modeling taxes in our case, so the maker's term won't really play any role. And yeah, let's get it going. So I just put in the inputs for some DC fast chargers, perhaps a suite of them that are all operated the same, that have a 50 megawatt power upper limit and need to charge 100 megawatt hours to some electric vehicles between some times in the afternoon. The other option that we had, the fleet electric vehicle option, we would have given it a time series charging profile. So for every hour of our year here, we'd give it a, what the electric vehicles in the charging plaza want to charge at. We would then give it information about when or under what conditions the charging plaza should rein in that charging and curtail it so that it could manage, well, either the energy value that we're considering here, demand charges perhaps would be relevant, or that kind of thing. So this single electric vehicle model was really built with like a single vehicle at a residence in mind, or some other very controlled case where we have good knowledge of when the system is plugged in, or when the vehicle is plugged in, and when it needs to be full by and that kind of thing. So in our case, that is a constraint, that is part of the optimization problem. It will need to fill the electric vehicle's battery every day at that level. So if we zoom back into August here, and maybe let's go to that peak time again. They overlap a little bit, but we can see the electric vehicle charging load in red now. It is about as peaky as it could possibly be. It's full 50 megawatts and then 0 for the rest of the time. So if this were a case with demand charges, we could perhaps expect that to be spread out a little bit more. But in our case, we see that it's very peaky, and it's chosen to charge when the energy price is lowest within the window it has to charge, which makes sense. So we can see the combined effect of our energy storage charging and discharging in brown here, and the EVs charging in red here in the net load profile up there. During the high price times, the energy storage system is definitely discharging as much as it can, and the site is exporting 50 megawatts of power. Then the EVs try to charge when the price drops a little bit within their window, and we start consuming power again. And where the two overlap, the charging of the battery and the charging of the electric vehicles, we see quite a lot of power draw at 100 megawatts up there. Overall, the interaction between the EV charger and our storage system didn't do very much to how we operated the storage system, since we're trying to minimize the energy charges here. But we can see a couple of extra steps here and an overall decline in the state of charge over these days that we didn't see as much of in the standalone case. One thing that Giovanni mentioned that we could have done at the beginning there was to put an interconnection limit on power flow. So for example, if we had put a 100 meg or a 50 megawatt interconnection capacity, we could expect to see the storage charging stop when the electric vehicles need to be charged and vice versa, so that we could manage that. But in most cases like this, we would apply a demand charge, for example, if this were some kind of customer facility, and then the charging load would spread out to minimize those demand charges. All part of this optimization problem. So I think with that, we can go and spend our last 5 minutes answering questions.
Thanks, Miles. Yeah, this is super interesting to see these results and the interactions here between the energy storage system and the electric vehicle. If anybody has any questions, feel free to either type them into the Q&A or you can raise your hand right now. But I'd like to start with one. Giovanni mentioned at the intro slides that one of the previous iterations of the tool influenced the California energy storage target. How do you see this more expanded DER tool being used to help policymakers and or state commissions?
Yeah, that's a great question. So from the beginning of when we were using mostly standalone storage in our analyses, we quickly started to see our utility members at EPRI and our work with governments and government projects quickly expand to not, it's really hard to just look at energy storage in a vacuum. So you're either comparing it to conventional solutions or there's hybrid systems like solar plus PV, or this case where if you're looking at a customer site, you might have multiple DER technologies. So, I think, as regulators take on, I think, more difficult questions of, deep decarbonization and, electrification, things like that, targets in, 2035 or 2040, 2045, you're going to have to look at that more holistic solution. The answer is going to be a little more nuanced and change a little bit as there's more flexibility and trade-offs between all the different technologies. And I think, this tool could also could have played a role in 2013 in thinking through some of that. But it can do either or both together now, and I think that's an important feature Unfortunately, it adds complexity to the decision maker's plate, but I think it's an important piece.
The energy industry is nothing if not already very complex. So I think we're all used to that part of it. One other question. So how do the IIJA and IRA incentives for energy storage or for DERs in general, how do they fit into this modeling? Do you update the model to account for these incentives, or is that up to the user to build into the inputs for the cost calculations?
So what we've done here is, and actually I didn't talk about it, but I actually, using our base case costs for the flow battery, I applied a 30% standalone storage ITC that you might expect from the IRA. But the way that we've handled incentives is to basically allow users to flexibly input whatever they'd like. So there's a whole tab here for external incentives that can either be specified in a file on your computer or very simply built up manually. We, of course, distinguish between tax credits versus grants or other incentives just for the tax implications. And we, these change by location so much and in time so much that we didn't build specific programs into Dervet and just left it as a simple input.
That's really helpful. I think that additional flexibility is useful because, as we know, things are changing really quickly, and they vary a lot from state to state too. There are some states that have, or even more local regions that have more higher or different or lower incentives than the federal incentives. But we have about 1 minute left, and there is one question in the Q&A that I'd like to get in. For the DC fast charge model, does the tool compensate for the likely possibility that charging is likely less price sensitive than the other customer loads? Assuming that a DC fast charger is likely used by a customer that traveling a long distance on a highway and stops to fuel regardless of price.
Yeah, awesome question. So this particular case here, where we had the well-scheduled DC fast chargers, we could have given it a binding constraint on when it needed to be charged by, and just had it charged fully until our vehicle was done. But the other one here, the other option that we have for electric vehicles, the fleet charging, we can specify how controllable the EV charging load is, anywhere from 0 to 100%. And if we say it's 100% controllable, then that means kind of the opposite of what you were describing, that we could curtail down to 0, or 0% controllable means this is just another fixed load without any interaction with our prices or other DER, that kind of thing.
Perfect, that's super helpful. Okay, well, thank you so much. I really appreciate the walkthrough of this demonstration, and appreciate everybody's input and choosing the direction that this simulation went in. Really interesting to see the final results come up on the screen live in front of us. So thank you for that. Sarah, I know that you have one final announcement for us.
Yes, thank you, Commissioner Peretick, and thank you, EPRI, for your wonderful demonstration. I'm just going to quickly talk about our upcoming innovation webinars. So the first one is on September 15th, 3 to 4 p.m. Eastern time, and it will focus on climate resilience with innovative wildfire mitigation technologies. And our October innovation webinar will be diving back into long duration storage, and that will be on October 27th from 3 to 4 p.m. Eastern time. So I encourage everyone to check both of those out by looking at our website, and also sign up for our CPI newsletter to get updates on other upcoming events and resources that we produce. Once again, a recording of today's webinar and a copy of the presentation will be posted on our innovation webinar website. Thank you again, everyone, for your engagement and attention, and I hope you have a wonderful rest of your day.